Good morning, everyone. This is Saloni Garg, and as Roman would already have introduced me, I'm a final year student from LNM Institute of Information Technology, Jaipur. I'm majoring in computer science, and today the topic of my discussion would be autonomous car driving algorithms and how we can use them for smart traffic surveillance. And what I mean here by smart traffic surveillance is basically traffic surveillance without the use of human, without the use of like traffic police department, and totally automating the process using OpenCV, computer vision, and image processing algorithms. Привет, I've just learned that. Good morning. Okay, so the traffic is increasing drastically, and that comes as a counter product of increasing population. The number of vehicles on the car we see are like increasing drastically. This in turn leads to the number of road accidents increasing, and like more cases of rash driving, more cases of deaths due to road accidents. And this like rash driving is one of the main reasons for road accidents. But other than that, like human error in surveillance also plays a role in this. So for example, like the traffic police department, the person assigned for a specific location, he might be engaged in some other activity and leaving the traffic unsupervised for a while, which might result in people not following traffic rules because there is no one to stop them or no one to like organize the entire traffic. So what we're trying to do is automating the entire process. For that, we'll be using four main aspects of it. First one is traffic congestion monitoring. So what I mean here by traffic congestion monitoring is basically checking like is the traffic in front of the vehicle very congested? Is there a very, very high traffic? Is the road already almost completely blocked? Or there are very few number of vehicles and the road is almost clear and there is very low traffic congestion? And why we are doing this in the first place is because when the traffic is very highly congested, when there are a lot of vehicles on the road, we'll have to increase our surveillance. We'll have to increase the protection. We'll have to process more number of frames per second, and we'll have to process traffic light violation detection, lane switching detection, with even more protection, with even more number of frames processing per second. The next one is daylight monitoring. So by daylight monitoring, I basically mean that we are checking is it day or it's evening, or the vehicle is passing through a shady tunnel, or like is the vehicle passing through an area with very high light or a low light. And why basically we are doing this? Because in case of low light, in case of shady areas or night times, evening times, so we'll need to again improve the surveillance, improve the security, and we'll need more surveillance, more protection, specifically for say women and children. We'll need more protection. The next one is traffic signals violation detection. So in traffic signals violation detection, what we are basically aiming at is detecting traffic lights on the roads and checking whether the vehicle that is under surveillance, whether or not it is like jumping stoplights, jumping red lights, or like the green arrow on the traffic light was for turning right, but the vehicle is turning left illegally. So that's what this part is for. And the last one is lane switching. So in this, we are first detecting lanes, and then we are checking if the vehicle is switching the lanes illegally. Like there are certain rules that define how you can switch the lanes in a particular highway or on a particular road. So this will mainly involve detecting the lanes. So without further ado, let's get started. First one is monitoring traffic congestion. So in traffic congestion, as I said, we're just checking if in front of the vehicle there are a lot of traffic or there's very less traffic. So our FOV, that is field of view in this case, will be multiple lanes in front of the vehicle. So when we are driving a car, we see that what we see like in front of the glass. It's multiple lanes with lots of traffic or no traffic at all, but it's multiple lanes in front of us. So that will be our field of view for the video. Basically what we are, how we are running this project live is we're mounting a camera device on a vehicle that will record the video what is happening in front of the vehicle, and it will be connected to a small processor that will be processing, that will be equipped with all our algorithms, that will be processing OpenCV and outputting the results. So for traffic congestion, we used YOLO version 3 to detect vehicles. So most of you, I think, will be already aware of what YOLO is. You only look once, and this is a very good object detection algorithm. We'll see more about YOLO and COCO dataset a little later in this presentation. This is a simple output we got from YOLO. So you see like these bounding rectangles on everything, like it's on a person, on a scooty, on a car, or also on trucks and everything, on autos, everything. So this is basically YOLO detecting objects. And once we have the number of cars in front of the vehicle, we can simply define our own parameters. For example, I might say like if it's 10 vehicles and the next 10 cross 10 area, so I'll define it as high traffic congestion. And if it's 5 vehicles in the next 10 by 10 area, so it'll be low congestion or medium congestion. So this is basically a sample output from YOLO. YOLO simply creates bounding rectangles, and that's how it counts the number of vehicles. So one of the problems that we faced during this process was that we were facing the problem of low frames per second processing, even on a PC, or even on a system with average specifications, on good specifications. So we were facing this problem of low frames per second. We weren't able to kind of process the real-time traffic data. So any one of you want to suggest like how we can solve this or how we can overcome this problem? Sorry? Smaller? Yeah, so we reduced the number of frames that we were processing. So the camera was giving us 26 frames per second. Like the camera was kind of good definition camera, and it was giving us 26 frames per second. And we reduced it to only 5 frames per second. Like we didn't want such high, number of frames per second. Why? Because if you are in a traffic jam, it suddenly won't, change to from high traffic congestion to very low traffic congestion. And this doesn't need to be monitored so minutely. So that's why we reduced the number of frames, and then our YOLO was running fine. Other than YOLO, we also tried HAAR cascade algorithm. So HAAR cascade is another object detection algorithm. But so how did we train HAAR algorithm? It was with positive and negative images. For example, for training HAAR algorithm, let me explain what HAAR algorithm does in the first place. So it detects any objects when trained for a particular object. For example, if you'll train HAAR cascade for a bottle, it will detect number of bottles in any footage that you pass to it. So we trained it with positive and negative images. A positive image of a car will be an image that contains car, and a negative one would be an image without car. And but what we saw that the most features that it detected in our videos were irrelevant, like they were of no use to us. So that was something that we didn't choose to finalize because it didn't have good, processing on real-time traffic data. So we chose to go for YOLO on COCO dataset. So COCO dataset, as you might be knowing, COCO dataset is trained on 330K images, a dataset of 330K images, and it can classify like up to 91 objects well. Like for example, if you'll feed a video of this room, so it will be able to detect the number of people, the number of males, females, the number of like laptops, bottles, etc. It very well detects 91 objects, that is common objects that it is trained for. So how YOLO stood out? It was extremely fast, and extremely fast for our PC with average specifications. So we also wanted to run it on a small Raspberry Pi that we'll be placing along with the camera in the car itself. So for that, we used fast YOLO. So what is fast YOLO? Is basically it compromises with the number of convolutional layers to like process a little less layers, but it was able to process our videos very fast, to detect the number of vehicles, to detect the number of buses, cars, and everything quite faster. The next one is daylight monitoring. So as I said, why we are like checking daylight monitoring, it's because we'll need high surveillance in the shady areas or in the evening times or in the night times. So how we went about it was, first we extracted a clip of a video that was recorded from the front of the vehicle. So we extracted a clip out of that. We reduced its frame rate. For example, the camera that was giving us 26 frames, so we reduced it to 5 frames. And we converted it to grayscale, and we calculated the average value over all the pixels. So to understand this simply, if we click a picture of this room when it's well lit, when all the lights are turned on, so, and versus when we click the picture of this room when it's very dimly lit, like when most of the lights are turned off. So what we'll see is that most of the what we see in this case is that the picture with very well-lit room will be very bright when converted to grayscale, so the picture will be very white, and the average value of pixels will be very high compared to the other case. So that's how we did it in this case. And we looped this for 5 frames. So why we looped this for 5 frames? Basically because we do not want to conclude that it's shady time or it's evening time, even when the vehicle is just passing through a small tree or under a small bridge, because then suddenly the value of daylight intensity would fall, but we do not want to conclude that the time has changed or anything. Next one is traffic signals violation. So for traffic signals violation, we used 2 approaches. First one was through blob analysis and morphological filters. So blob analysis was pretty good at detecting arrows. I'll just show you. So this was blob analysis. This is a traffic light, a very close image of traffic light, and it was very well able to characterize that which side the arrow is pointing to. But it didn't work well on traffic light detection. So this is an image converted to grayscale, darkened, applied Gaussian blur. So this doesn't tell us where the traffic light actually is. Why? It just increased number of false positive. It wasn't able to detect the traffic lights that were very far away from the car or from the camera that we've mounted on the car. More than that, even if we feed in an image of a very close by traffic light, it wasn't able to detect whether the current light is yellow or orange or red or green. So the limitations that we faced was extra bright spots were detected, and like if there's a small light in bushes, it would detect that as well, and number of false positives increased very, very much. This is an example. So what approach we finally chose for detecting traffic lights was using image processing. We dropped the idea of using computer vision for this because it was not kind of accurate. And we detected traffic lights using computer vision. We removed the background. And then we detected the shapes, the circular shapes. And then we converted the image to HSI image. HSI, that is hue saturation intensity. So after converting it to HSI image, we were able to detect which one of these is active. Like currently, is it red, or it's yellow, or green? Then we found out relative spatial information. That was also primarily done using image processing. So Relative special information, I mean how far is the traffic light from the car, so that we can detect whether the car is crossing the red light or it's standing very far back from the red light, because ultimately we want to only detect and only raise a signal when the car passes the stoplight. So detect stop line. The last one is lane switching detection. So in lane switching detection, what we are going to do is basically detecting the lanes in which the vehicle is driving. And why we are concerned with detecting the lane is because there are specific, I'd say, rules, traffic rules defined that you can only switch a lane in this case or that case. So that's why we need to detect the lanes. For detecting the lanes, this was the approach that we used. We first converted the image of the field of view into grayscale, and then we darkened the grayscale image. We applied Gaussian blur, we applied canny edge detection, selected region of interest, and half transformation. We'll see that one by one. So this is the original image, and what we want to do is basically detect these lanes. More specifically, we want to detect the lanes that our vehicle is driving in. So we first grayscale the image. Why we grayscale the image? Because this is generally taken into account that if there's a black road or if there's a very dark road, the lanes would be yellow colored or very bright colored. So we are trying to figure it out using that. The color difference between the color of the lane and the color of the road. We converted the image to grayscale, and then we darkened the grayscale image. You see the differences of colors between the road and the lanes got even more intensified, even more better, accurately observed. Then we applied Gaussian blur. This is even more properly put. We can detect the lanes more easily. Next is we applied canny edge detection. So what canny edge detection is, it was found by John Canny, and it just detects the edges in the image. So you see it detected all these edges as well, all the edges that it can see in an image. This is also used in lots of phones, AI cameras, for example, Pixel's AI camera also uses this. So this is Gaussian, this is after Gaussian blur, and this is after canny edge detection. So it detected all these edges as we see. After that, we just selected the region of interest. The region of interest was our own vehicle's lane. We are not even interested in other lanes because we are just checking if our vehicle changes lanes, our vehicle changes lanes. That's all we are concerned about. Next, we applied half transformation, and after half transformation, this is what we've got. So what half transformation does is, it just simply, half transformation earlier was about detecting lines in an image. These days, it has also been modified to detect shapes like circles or squares in something. So this just detected the lines in that image after region of interest, and it connected those lines, and this is the output that we got. I think I'm unable to play the video. Or we can just give up.
Maybe you should press F11 and open new tab with video, just shows the video, just come back.
Okay, you can just leave. Let's play this. Okay, so this was mainly a video that detected that as our vehicle drives, as it goes further, so it was able to detect the lane on the go, like real-time lane detection. Spicy bow.
Да, зададим вопросы какие-нибудь. Да, пожалуйста. Так, а вот микрофон уже идет. Сейчас все будет. Да.
Thank you very much for your presentation. I have a question about instance detection. So like you showed...
Sorry, instance detection?
Yeah, so like you have these bounding boxes for the cars.
Object, yeah.
So as I understand, for me it was not clear if like you keep the information that this object appeared on previous frame. So like you have this information. If you have this information, for example, why didn't you apply some kind of Kalman filter? So like you can track the objects between frames. So like you can reduce the like CPU time. So like you can compute the location of the bounding box every several frames and just interpolate between these computations with Kalman filter.
Okay, as much I understood, it was like, should I like
Yeah,
keep
like
the track of frames in the previous frame, keep the track of the objects detected in the previous frame, and just kind of apply translation of objects so that I do not have to entirely detect objects in the new frame,
Yeah,
like to save processing power or something?
Yeah, it was the question like, why did you choose this approach and not, for example, some other approach?
Yes, so we tried it with two approaches. One was HAAR, which was like we ourselves trained the algorithm for cars and for trucks. And then we tried to use that, but we were not able to do it so efficiently that YOLO was already trained. So YOLO is basically an open source project, and it has been contributed by people from all over the world. So they were obviously able to do it better than us. So we tried to go with that. Do I have metrics?
Yeah, like how to compare YOLO and...
Yeah, so like it was, the results were very straightforward because we ran a HAAR trained model on one of our videos collected from real-time data, and it was not able to perform well. So it was like straight away rejected. HAAR cascade.
Да, пожалуйста, вопрос еще там. No. Раз.
Thank you. First of all, thank you for awesome presentation. And I have two questions. First of all, did you use Python here? We all know that Python is too slow. Can we use it in production, for example, where we need to do in real time on big speeds? And the second one, for some basic Gaussian blur and other, did you use OpenCV library or some another maybe? Thank you.
Yeah, we used Python and we used OpenCV. So this was mainly because most of the developers that were involved in the project knew Python, so we chose to go with Python. And yes, we used OpenCV.
I got it, thank you.
Other questions? Yeah?
Hello, thank you for your presentation. What do you think about future of self-driving cars in winter when it's snow?
So like this kind of scenario is not very common in India. So like yeah, so I believe I'm not the right person to answer this.
Okay.
Sorry.